Swayam Prabha. Digital India. Educated India.
Now you integrate this guy. So you integrate it, put whatever are the limits that you want to put in. Let us say you put it between some P naught and some P, and okay, this is kind of restrictive, but you can go with it. Or you can just say at x equal to x naught and y equal to y naught, p equal to p naught, whichever. That's perfectly fine. Okay. So in which case you would have an x minus an x naught hanging in here, a y minus y naught hanging in there. Okay, that's about all is going to be the difference. So what you have is now the variation of pressure with respect to x and y, right? When your frame is accelerating with an acceleration ax and an acceleration ay. So that's what is given up here. So now what happens to the free surface? I've got this vessel. I originally was having something like so. I accelerate this guy, and what you're going to see is that there is going to be a profile like this. Okay. So this is atmosphere, this is liquid, and this is a linear profile. Okay, that's what my equation is telling me. Okay. If there is a free surface and P is equal to P naught, which is what is here. There is a liquid in a vessel. The vessel is accelerating. There is atmosphere here. And you are going to get the math is telling me that this guy has been colored in red because I can easily put this equal to 0 if P is equal to P0. And this guy is gone. And this is the equation of a line which is a straight line, right? So when this fellow is moving like this, okay, I am drawing the profile like that. Is it possible that the profile is like this? Is this the profile or is this the profile? Let me say this is A, this is B. Which is the profile, correct profile?
Sir, A is the correct one.
A is the correct profile, right? The equation is telling me that. The equation is clearly telling that y is equal to minus mx, right? A is positive, G is positive, A is positive. Y is equal to minus mx. So this guy is not the profile that you are wanting. So mathematics has told you that the profile will be linear. Mathematics also tells you that the profile is going to be like so. Okay, so this is one example. Let us look at another example. The other example that we look at is a container that is rotating about its axis. So there is a container like so. I have liquid filled in the container and you are rotating the container. What is going to happen to the profile? Okay, so can anybody tell me what now is going to be the equation that we will write? Grad P is equal to rho x. Okay, what is x now? There is G here. Okay, so there is going to be some I component and some J component. Okay, so let me just say that you have got an R and a Y. So R is equivalent to the I direction and J of course is equivalent to the Y. So what is going to be in the J direction and what is, so once again you will take a small element here. Okay, so what is going to be the force that acts on this element? What is the force that acts on that element?
Centrifugal force and
Cent
gravity.
Centrifugal and gravity. Okay, very good. So what we have is, if I'm talking about this, this is centrifugal and this is gravity. Okay, now let us put in values so that you can do, this is a qualitative answer which is correct. Let us put numbers so that we can evaluate something. What about this here? What is G?
The numerical value or like in terms
No,
of
no.
G?
In terms of G,
So it will be minus G
minus G. That's what I'm looking for. So I've got a minus GJ. Okay, what about this guy here?
in the
R
R
omega
with
R?
X omega.
Okay, X omega or omega
square.
square. If you want to call it R omega square, X omega square, whatever. Okay. So the centrifugal force we all know is M omega square R, and therefore we are talking about this guy here, and this is per unit mass, and therefore we'll put this here and we'll have a G, that a rho that is going to be sticking in there. Okay. So once you have written this, the rest is just brute force algebra. Okay. So what you have is dP, once again, grad P is equal to del P del xi del P del yj, correct? And del P del y is minus rho g. This is minus rho g j. And can you help me with the sign SIGN of omega square r? Is it plus or minus?
Plus.
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 Right. So this is plus omega square r, and then I put my rho in here. Okay. So grad P is del P del x equal to rho omega square r I, and del P del y is minus rho g j. Okay. So now the rest is straightforward. Go to your calculus. dP is del P del y dy, del P del r dr. So dP is equal to minus rho g dy plus rho omega square r dr. Go ahead and perform the integration and you get P is equal to this. Okay. And if P is equal to P naught, which is a free surface, which is what is being shown here. So if you are talking about a situation where, let us say, this is P air and this is, say, rho water maybe, and if you are going to rotate this, you are going to see an interface that is going to be coming in, which is, so this is an experiment that you're going to be doing in the lab in the next semester. So this is a perfect parabola. Okay. So if you want a perfect parabola, you just take a bowl of liquid and then you rotate this guy at constant speed and you are going to get a perfect parabola. And apparently some of these celestial telescopes which require absolutely perfect parabolic surfaces use mercury as the liquid, and then you rotate this mercury and you get a perfect parabola. But that's an aside. Okay. So as far as looking at situations is concerned, I think we will stop there. And the next thing that we are going to be looking at is some examples related to what we have seen so far. Okay. So anybody have any major problems now? Okay, in terms of the material that has been looked at. Okay, so we have looked at in today's class and in yesterday's class, we have looked at something to do with buoyancy and something to do with stability and something to do with a situation where um, the acceleration due to gravity is not the only body force. So these are the three things that we have seen. And We will now try to go ahead and take up a few examples so that we understand the material a little bit better. Okay. So if there are no questions, we'll go ahead and start looking at the examples. Anybody have any questions at all? Okay, very good. All right, so let us take some examples so that we can understand what we are doing a little bit better. All right, so here are a couple of examples. We start with buoyancy. There are two cubes, okay? So there is one cube is sitting in here. This is one cube, okay? The cubes are of the same size, 1 meter cube. One is of specific gravity 0.8 and the other is of specific gravity 1.1. Okay. Both are connected by a short wire and are placed in water. What portion of the lighter cube is above the water surface and what is the tension in the wire? All right, so we have been given two cubes. The specific gravity is given, which means that the density is either 0.8 rho W or it is 1.1 rho W. So this is the top cube. This is the bottom cube. Okay. All right. All these fellows are all submerged in a liquid, which is water. So what portion of the lighter cube is above the water? How do we go about doing this? Anybody? How do we go about trying to figure this out?
Free body diagram of individual.
Okay. So you can do a free body diagram of the individual guys, or you can do a free body diagram of the combined fellows. Because we are talking about the portion of the lighter cube, and if you take the free body diagram of the individual fellows, then tension becomes another unknown. So to start with, let us take the free body diagram of the two combined together. All right, good. So let x be the height of the lighter cube above the surface of the water. Okay. So you have the above cube and you say that this is x. Okay. So what is going to be the net downward force and what is going to be the net upward force? So will there be a net upward force on this cube or a downward force? This is the top cube. Remember, the top cube is going to experience a buoyancy force and then there is going to be a weight, correct? If the top cube had been left alone, if the top cube had been left alone, it would be happily floating, right? But somebody has pulled it down. Okay, so will it have a net upward force or a net downward force with respect to its weight? The top cube has been submerged in water more than it wants to. This is its equilibrium condition. Now somebody comes and says, hey, I don't want you to float like this. I want you to float like this. Which means that somebody is putting a force like this, right? Which means that this guy is going to experience a net upward force. Right? And the bottom cube, correct, is anyway going to experience a net downward force. So the bottom cube is going to get a net downward force. The top cube will get a net upward force. The upward force on the top cube is going to be the buoyancy force minus the weight. The buoyancy force on the top cube is going to be rho g v, where v is the submerged volume, right? What is the submerged volume? We have said this is x, this is 1 minus x. So 1 minus x times the area of cross section. So this is the upward force that is coming on. So this is rho, this is g, this is 1 minus x, and A is equal to 1 square. So this is the buoyancy force, and this is the weight, right? This is the density times the volume. So specific gravity times the density of water times G times the volume, which is equal to 1. So the net upward force on the top cube is going to be this number here. What about the net downward force on the bottom cube? The net downward force, so the bottom cube is there. What are the forces that are going to be acting on the bottom cube now? The bottom cube, okay. So I have got a bottom cube now. I've got this fellow who is sitting in the bottom here. Now there is going to be a weight that will be coming onto it. There will be a force of buoyancy that is going to come onto it, correct? And there is going to be a tension, but the tension will cancel off because we are taking this body and this body together. So the weight of the body is going to be 1.1, which is times 1000, which is the density, rho. Then you have got a G, then you have got a V, and the V is 1. Okay, so 1.1 rho G V is going to be the weight. And then there is a buoyancy force. How much liquid it is going to displace? It is going to displace everything which is equal to its volume because it is fully submerged. The bottom cube is fully submerged. So the V submerged is equal to 1 meter cube. So the V submerged is 1 meter cube. So you have got 1 times this times this. Okay. So the volume is missing here. The volume is equal to unity. Volume is equal to 1 meter cube. Okay. So the net downward force on the bottom cube is this. The net upward force is this. At equilibrium, both are the same, and therefore the net upward force, net up, is equal to F net down, right? And this is going to tell me what this X is going to be. You can go ahead and do the algebra and you can get X as equal to this. Now you can go ahead and look at the tension in the cable. You can take either the top or the bottom, whichever it is, whichever you want to do. Okay. So the tension is the net upward force is going to be equal to the net downward force is equal to the tension. So the tension in the cable you can easily calculate as being equal to that. Okay, so anybody have any trouble with that? So fairly straightforward stuff. What we have seen is there is a body, and what we have said is that we have a cable in between, and the cable is under some kind of tension, and initially we took the full free body and we obtained the value of the submergence, and then we got the tension. So anybody have any trouble with that at all? Okay, very good. So let us now look at the next question. Okay, a cone floats in water with its vertex downward and its base horizontal. Okay. It has a base diameter of d, vertical height h. If the specific gravity of the cone is s, show that for stable equilibrium, something is to be shown. Is the question clear? Is the question clear? Okay. There is a cone. Okay. So there is some kind of a cone. Now, so this guy is my cone, okay, and it is submerged, which means that this is something like this, which is submerged. The vertex is downwards and the base is horizontal. So the base is horizontal, the vertex is inside the water. The base diameter is d, the vertical height is h. Okay. So the vertical height is h, the base diameter is d. Okay. And the specific gravity of the cone is given as s. Show that something for stable equilibrium. Okay. So is the question clear? Anybody?
Yes, sir.
Yeah? Okay, fine. The question is clear, so now let us go ahead and try to get the solution. Okay. So what would be the approach? The approach would be what we had seen just a little while ago. Okay. So we had said that we are going to perturb the body and we are going to find out what is going to be the MB that we talked about. So a little while ago, we talked about something called the MB, and we had shown that MB is equal to I by V, okay, where I was the moment of inertia at the wetted perimeter of the surface. Okay. So what is going to be the wetted perimeter of the surface? Suppose I say that this is something, I don't know what I have called it. Okay, I have not called it anything. So let me just say that this is equal to, let us say D1. So what is going to be the wetted perimeter when it is stably floating? What is the wetted perimeter? What is the wetted perimeter at stable? Wetted perimeter equal to what?
It will be the circular region
It will
whose
be the
diameter is
circular
given.
region, right? So the wetted perimeter is going to be the circular region. There's no question about that, right? Okay. The reason why I am asking you about the wetted perimeter is because we need to be very clear about where to take the moment. That's the reason why I want to. The wetted perimeter doesn't play any role actually. Okay. All right. So the first thing that we need to do is to say that now the cone is floating and let the cone float, correct, with height x under water. Okay, so let my cone be there and so let the cone float with height x under water. So this is my cone and this is x under water. Okay. So what we need to first figure out is we need to find out what this diameter is, and then we are going to get the moment. So what is the shape of the area for which the moment is to be computed? Because remember we said that I need to get an I by V. Okay. I is for what shape in this particular case? Is it triangle? Is it rectangle? Is it circle? It is a circle. Okay. So the wetted perimeter is a circle at the surface and the shape is going to be therefore a circle. All right, very good. So let the cone float with height x underwater. So now we just use the simple principle of buoyancy and we say that weight of the cone is equal to the weight of the water that is displaced. What is the weight of water displaced? weight of water displaced is going to be, what is the weight of the water displaced? Volume of the cone is, suppose I say this is diameter d1. What is going to be the volume of the cone? 1/3 area of the base, right? Right? Multiplied by x, multiplied by rho times g. This is the buoyancy force, right? Everybody agree? The buoyancy force is going to be the weight of the volume of the submerged body. The volume of the submerged body is this here, 1/3 area of the base into the height multiplied by rho g is the buoyancy force. What is the weight? The weight is going to be 1/3 area of the base, which is d, multiplied by the height, which is h, 1/3 area of the base into the height, multiplied by rho g, where rho is now of the solid. Right? So the specific gravity of the solid has been given as being equal to S. Density of water is rho W, and therefore this rho solid is going to be equal to rho W times S, which is equal to this. Okay. Now, this is the same as this, is equal to the buoyancy force, which is rho W, 1/3 area of the base. Okay. So D1, right, this is straightforward for you to figure out. D1 is dx by h. Right? D1 is dx by h, and therefore you have got dx by h square multiplied by x. So d1 is dx by h multiplied by x. Okay. So you go ahead and do the algebra, and what you will get is x is equal to h s to the 1/3. Okay. So the area of the cone that is going to be submerged, the height of the cone that is going to be submerged is obtained in terms of the height of the cone and the specific gravity of the cone. All right. So the next thing that you want to understand is what is going to be this business of stability. Okay. So the buoyancy part is done, and the next is the stability part. Okay. So what we have said is this is my cone. This is floating like so. I have x like so. And I have already determined that x is equal to h s 1/3. So this I have determined by using the principle of buoyancy. So this is h. Okay. So where is going to be g now? We need 3 points, right? We need a g, we need a b, and we need an n. Okay. So these are the 3 points that I am going to be wanting to have. And what now we are saying is that if I'm going to compute what is going to be this m here, then I can get what my stability condition is. So the stability condition is mb must be greater than bg. Okay, so mb must be greater than bg, or mg is greater than 0, whichever way you want to look at it. Okay, so what this gives me is mb. So mb, okay, so first what is g now? G is going to be here, correct? Now, can you physically say why G is going to be above B in this particular case? Anybody?
Because major portion of the mass is increasing Right.
So major portion of the mass appears to be here, right? So there is going to be a bias towards this side for the G. And the center of buoyancy, of course, is going to be the submerged portion. So it is going to be somewhere there. Okay. So we all know that for a cone, this is h by 4, correct? And likewise, therefore, this becomes x by 4. Right? So we know this, and because we know that the center of gravity of the cone is h, but what I want is this here. Therefore, what I say is all right, that's all fine, but the base is not fixed. That's what is being written up here. The base is not fixed, but the vertex is fixed, right? So let me go ahead and do this here. Of course, some of you may think of it as 3/4 height from the vertex. That's perfectly fine. So the BG becomes equal to 3/4 h minus x. Okay. So this is fairly straightforward. So the B is the center of buoyancy. G is the center of mass or the total volume or the mass, if you will. Okay, so Bg is 3/4 h minus x. Okay, so the last thing that we need to figure out is what is Mb, and Mb is I by V. And what is I now? I is going to be the moment of inertia of a circle with what diameter? If I'm going to call this a D1. So this is D1, right? So, and if you look up a table of sorts, you will get the moment of inertia is pi d4 by 64. So this is going to be about which axis now? It is about this axis here. Sorry. So the moment of inertia is going to be about the axis in which it is rotating. Suppose I tell you, suppose the body was like so. There was a body like so, and there was a body like so. So this is B, this is H. Okay. Now, and for this also, this is B, this is H. This is B1, this is H1. Okay. So what is going to be I for this case for determining I by B? And what is going to be I for this case for determining I by B? Okay. I is equal to what? In this case, what is I? Is it BH cube by 12? Remember, if I have a thing like so, and this is B, this is H, it is BH cube by 12. Now, what is the axis about which I need to take this moment? Is it this axis or is it this axis? This has to be very clear. So this, let us say, is x, x, this is y, y. And this is the surface of liquid. Am I supposed to take I, y, y or I, x, x? Is this I, x, x, I, y, y? Which one of them is going to be there in this particular expression, in this expression here?
I, Y, Y.
I, y, y.
I.
Yes. That has to be very clear in your mind. Okay. So the IYY is something that you should be taking and not IXX. So if that is clear, then I think everything is clear. So anybody not clear about what is the axis about which you need to take the area moment in this particular expression? The rest is just brute force algebra. Yeah, continue.
Sir, could you once explain how it's YY?
Okay, see what we are saying is, um, let me just erase everything. Let us go back to our derivation. Okay, that's much easier there. Okay, so here is my thing. Okay, so why is it that I am taking a particular axis and not another axis? Okay, so in this particular case, let me just say you have got this, right? And this is my submerged thing. Remember, I said that there is the wetted perimeter here, right? This is the body. This is the wetted perimeter. Okay. What you see in the dotted line is the wetted perimeter. And when I'm going to perturb this here, what is the axis about which this rotation is happening? It is this axis, right? Right. In this particular case, it happens to be ZZ. Okay. So the axis about which the rotation is happening is the axis about which the moment of inertia needs to be taken. Okay. So the axis about which the rotation happens. Okay. Now let us go back to our question here. Okay, for this circle question, there was no issue. That's why I brought this other fellow into picture. So now here is my body. I have got a two cross sections. One is like so and the other is like so. And this is the liquid surface. Okay. And if you look at it, this is the cross section of the body, and this has to be the axis about which I am taking the moment and not this. Okay. So if you are talking about the stability of the body when the perturbation is in this direction here, okay, then yes. Okay. So I must also tell you, right, if I give you a body like this, am I talking about the perturbation or the stability of the body in this plane, or am I talking about another plane? So therefore, in this particular case, there was no confusion because it's a circle, and therefore all directions are pretty much the same. Okay. Okay. So our time is over. Is that clear now?
Sir,
Yeah.
sir, can you explain why the perturbation occurs from the center of the point O itself?
What we are saying is that I am just having a body which to start with is symmetric, and I'm just giving it a force in one direction, and therefore that is up. That's all I'm saying. Okay. Remember, all these deflections are small deflections. They are not huge deflections. Theta is a very small number, which is why we are saying um, uh, theta is equal to sine theta equal to tan theta.
No, sir, my doubt was why the perturbation occurs about point O only.
It's a symmetric body, right? It's a symmetric body. So I'm going to say that I'm going to perturb the body and it is going to move in a particular axis, right? And that is going to be the central axis of the body. I'm perturbing a body, right? And it's a free body, right? It has no, it is not tied up anywhere in any sense, right? So if it's a uniform body, then it will perturb itself in a uniform fashion. That's what we are saying. This is a model that we are using. Let me just close the recording.